Welcome to another episode of Baz Codes. I'm your host, Baz, the great and powerful. Or not. Maybe just great. Uh, I've been away on vacation for a while, just got back not too long ago, and I'm getting back into working on my emulator, GSSquared. And what I've been doing is working to integrate contributions from a gentleman who pitched in, and we've been working on cycle accurate video. Now, I'm going to clear that because that's just a little bit annoying. Okay, there we go. Um, uh, as you may know, or may not, depending on how deep into this Apple II rabbit hole you've gone, um, the Apple II video and the CPU clock are very tightly interrelated on the Apple II. And one click of the CPU clock generates 14 dots of display information, or in the standard, 40 column text in high res modes, it's 7 pixels on the display. And that relationship is hard and fast fixed. Modern computers, there's no relationship at all between the video circuitry and CPU clocks. But on the Apple II, everything derived from the 14 dot, something megahertz crystal that was divided to generate the CPU clock, all the video timing signals, all that stuff. So it became possible to count cycles executed by your code very, very carefully, and to then switch display modes on the fly. So you could have a part of the screen be in one mode, say text, and then a different part of the screen in another mode, say low res, and then switch to yet another mode. And depending on how carefully you constructed your timing loops, you can generate all kinds of interesting effects. Now, in my original development on this, did not focus on what I'm calling cycle accurate video. I was more interested in focusing on just raw performance of the different components. And handling cycle accurate video did require rethinking a number of elements in the video display logic, which I haven't fully resolved, how I want to handle that in the long run, because I do want to be able to have, at the end of the day, my 400 megahertz Apple IIgs and run productivity software at reasonable speeds. But for running, existing Apple II plus 2E type software, and it's at one megahertz, there's lots of room to be inefficient based on my prior work. So let's start with, I think, the little sort of demo program that started this all, which was a small sample program in Jim Sather's Understanding the Apple II. All right, so let's do this. So what the Sather book had was this little program that draws some stuff in high res and low res, and it's actually got two purposes. One, it's demonstrating certain cases of high res NTSC artifacting. So you'll know that the Apple II standard high res mode only has black and white, and then 4 colors: violet, blue, green, and orange. right? But what you see on the screen here is a lot more colors than that. We've got kind of bluish, another blue, greenish, I don't know, bluish purple, yellow, pink. These are not normal high-res colors, but we just drew on the high-res screen. So if you put the right dots in the right place, you can generate these artifact colors. So one purpose of this Sather demo was to show how these matched low-res colors, right? And so that's what we got here. And this is the kind of the low-res color number. If you were to, draw the low-res graphics, this is the color equals you would use in AppleSoft. So he's doing a very straightforward loop here. It's like half of the loop is it's switching between low res and high res in mixed mode. So the bottom is just mixed mode text. That's why we have text down there. And then he reads the keyboard and gives you the opportunity to kind of delay the whole thing a few cycles so that you can move the position of the split between low res and high res just by delaying it. He's not checking for vertical blanking or anything here. The original Apple II Plus, when he wrote this, didn't have a VBL, a way to read VBL. So he just hit a key. And so I think this was like the first time anybody really demonstrated this technique. I won't call it a mode. It's not a mode. It's rapidly switching between modes. And this is the first time GSSquared has had the ability to correctly display this technique. All right, so a couple of things while we're in here. One of the other things I've added to GSSquared recently is a different approach to an RGB mode. So what we're looking at right now is NTSC. It's simulating an old-time, composite NTSC monitor, and the color derives from just essentially interference between a signal coming out from the Apple II and timing, color timing in the monitor. That's how you get these artifacts. Even though the Apple II didn't normally display these, you could kind of emit the right bit patterns in the right places to get these other colors. But I've added an RGB mode, which is this. I had a different RGB mode, which was just based on me manually trying to do, what programmers would have done at the time, like just kind of programmatically detect what the color was supposed to be. This algorithm I actually took from a patent Apple filed in 1988. I think it's how the Apple II GS actually generates its RGB output version of high-res displays. So you can see here, we still match, we still get the artifacts, we still match the low-res colors, and everything else still works here. And of course the pixels here are not blurry. In NTSC mode, it takes time to fully shift from one color to the next. In the RGB mode, it's much more distinct, the pixels are. And this is, of course, monochrome. And you can see these are the bit patterns that are being used to generate, these colors. You'll see here, here's 2. And then, let's see, 2 dots, and then 2 ones, and then a 0, and then maybe 2 more 1s. And this is how we generate yellow, right? And that will correspond to this, right? So this was yellow up here. So it's 2 dots, and a 0, and then 2 more ones. And so that's how, Sather determined that you could replicate some of those patterns in high res to get these unexpected high res colors. All right, so after this, I don't recall that there really was much in the way of use of this technique until well after kind of the end of the original Apple II era and the beginning of the new Apple II hobbyist era. And so I'm going to switch now to a program I found called Fireworks that demonstrates this technique with some stuff going on. Because before it was just static, right, image, and that's fine. That's a static. That's relatively easy to count cycles when all you're doing is switching between different static images. But here we're animating. Somehow they're animating this text, and I'm not clear on how that's occurring. This might just be text, and then they quickly switch back to a graphics mode to have the lines through the text. But I'm pretty sure this is just text. And then they've got this animation going on up here in the top half. And some sound. It's just very short clicks, right? It's about what you can get away with, given a relatively small number of cycles you have to play with before the next frame starts drawing. But this is really impressive. This was written by someone whose name I've seen around, Dieter. Let me know if any of you know who Dieter is, or if he's still active. And this is cool. This is about all it does. Of course, all of these techniques, because you're counting cycles, the video is tied to the CPU, and so you have to count cycles very, very carefully, and it has to be 100% accurate. If you're off by one cycle, everything on the display is going to get shifted inappropriately. And so, that's really limiting in terms of what you can do outside of that. All right. So taking this technique up a notch, I came across this one, which is called the split screen demo or just split demo. Fun. All right, VRun. Well, that's interesting. So one bug with this program, it's not setting the full screen. So whatever the full or mixed mode was set to before, it keeps. And then also, there's something going on with the mocking board where certain of the channels don't have the right volume. Maybe it's not setting those either. I'll reset and rerun and see if I can get this to play audio better. Okay, that's weird. So now that channel has volume, but the other ones don't. Okay, well anyway, you've got some Mockingboard music going on here. Probably interrupt driven. Maybe not. I haven't looked at it too closely. The top is text. The middle part is high res. And then the bottom part that's being animated is low res. yes, cycle counting is hard. Let's boot this one more time and see if we can get the music playing a little better. It could also be a bug in my Mockingboard implementation. Yeah, it's... Okay, well... Now there's 2 out of 3 channels that are playing music. Okay. Well, anyway, so this is sort of a notch up, right? They're animating in low res, so it takes a lot less cycles to draw low res than draw high res, of course. Okay, I don't know why I just stopped there. That's weird. You can just barely hear it in the background. All right, so that's a pretty cool demo. But we're getting ready to crank this up a notch because French Touch is in town. All right, these guys really took this technique to a whole nother level, as you'll see. So here, I think this is 2 different high-res pages, right? Like page 1, page 2. So they've got the one image on page 1, the other image on page 2, and then they're drawing the box that's sort of peeking through on every scan line here. So they must be doing some really radical, like lookup tables or something to determine where the box is. I don't know the details of the code. Maybe one of the French Touch folks could step in and make some comments about how they did it. Oh, poor Homer. Yeah, he's always getting in trouble, isn't he? So this is switching between like high res and text. I think that other one was high res and low res, perhaps. And they're changing the whole, screen. Because here they're changing the colors on the low res. They're changing the text. The previous slide, they were, spelling French Touch out in text. So that's like, 1,024 bytes that they're writing out. This one is a mix of text and high res. And actually, this demonstrates a bug in my approach. You see how the F and the T are sort of slowly moving up the screen. Also, they're a little jerky. So that's not how this is supposed to be displayed. I'm about 90 to 95% where this needs to be, but this particular one shows shows one of the places where I still have some work to do. All right, so that's going to start over. Now, they did this, maybe it was like back in 2015, 2016. Some years later, they came out with Crazy Cycles 2. Crazy Cycles 2 requires, actually probably both of these work better on the 6502 versus 65C02. That's some double low res right there. Okay, so here we've got some pretty aggressive Mockingboard music. And they've managed to split the screen into these tiny, relatively small blocks and to independently manipulate them. This is the same idea, splitting or going back and forth between page 1 and page 2, but with a lot more control down to these squares, or however many that is, like maybe 12 by 8 or something. Now this is going between high res and low res, but they're doing the low res switch only for a short time, so it's this cool effect. So I think you'll agree this is really stepped up a notch here. Now this this here is a little bug that I got to resolve. This should be going all the way across the screen, I assume, but something's probably 3 cycles off here, for whatever reason. It's probably the same thing as before. And I've got an approach I know I want to take with it that should resolve both of these. Okay, that was Crazy Cycles. Now, of course, this stuff's not useful for games, probably. It's just too hard to do cycle counting and do other stuff. You can't even read the joystick on an Apple II in a fixed amount of time. It's variable depending on the position of the joystick. So, this technique is okay for these sorts of demos, but you're not going to use it in application software or even typical games, except for maybe title screens or things like that. But it's cool, right? And it shows the level of control that these old computers had over the hardware. This would be very difficult to do. I mean, getting these effects by modifying the display hardware on the fly, it would be impossible on a modern computer, especially where the video system is completely decoupled from CPU timing, and you can't even hardly count cycles on CPUs because you don't know what's going to happen with cache. The same instruction might take different amounts of time just depending on what else is going on in the system. So this is an art that's really relegated to these old 8-bit machines, and aren't we glad we had them? All right. Thank you. Thank you to William for your contribution of the cycle accurate code, and thank you to all of the demo writers over the years who produced this cool stuff for us to check out on our Apple IIs. Hey, have a good one.